Most parents think Lego is about dumping a bucket of bricks on the floor and seeing what happens. But there's a parallel world where those same plastic pieces teach Python programming, sensor fusion, and the kind of systems debugging that gets teenagers hired for engineering internships. I'm Rajiv Patel, and I've spent 15 years watching companies struggle to find entry-level engineers who can actually integrate hardware and software. Turns out, the solution might be sitting in your kid's toy bin, if you know which sets to buy and how to use them.
You're listening to the STEM Lab podcast. Quick heads up before we get rolling. Everything you hear in this episode, the research, the data, the script, all of it comes from real human authors who verified every detail. The voice delivering it, though, that's AI generated. Just want to be straight with you about that from the start. If you've been listening for a while, thank you. Honestly, it keeps us going knowing this stuff actually lands with people. And if you just hit play for the first time, welcome aboard. We're here to cut through all the hype around STEM education and focus on what genuinely builds technical skills. New episodes come out every Monday, Wednesday, and Friday. All right, here's what we're getting into today.
Lego STEM education represents a structured approach to developing mechanical engineering, programming, and systems integration capabilities through modular construction platforms. Unlike recreational building, these systems establish progressive competency frameworks aligned with industry hiring requirements. The market shift from consumer toys to credentialed learning platforms matters because employers now require demonstrable skills in CAD modeling, logic-based programming, and hardware-software integration. Lego's education ecosystem specifically targets those capabilities. Let's start with what Lego STEM education actually is. It comprises three distinct product lines: Lego Education, which is classroom-focused kits with curriculum frameworks, Lego Technic, emphasizing mechanical engineering, and Lego Robotics platforms like Spike Prime and the EV3 successor systems. These aren't generic building sets. Each line delivers measurable learning outcomes through structured lesson progressions, assessment rubrics, and compatibility with industry-standard software environments. The differentiation matters. Lego Education We Do 2.0 teaches Scratch-style block coding and basic sensor integration for ages 7 to 9. Spike Prime advances to Python text-based programming and multi-sensor decision trees for ages 10 to 14. The discontinued Lego Mindstorms EV3 established the robotics competition standard but required significant adult facilitation. Spike Prime reduced that friction while maintaining expandability. Here's the technical foundation. All current platforms run proprietary block-based environments that export to Python. The software operates offline, which is critical for schools with restricted networks. It runs on Windows 10 and higher, macOS 10.14 and higher, iOS 10.0 and higher, Android 5.0 and higher, and Chromebook. There's no cloud dependency for core functionality. Storage requirements are 500 megabytes minimum. For lab specs, power comes via rechargeable lithium-ion batteries with 8 to 10-hour runtime and USB-C charging. Bluetooth 4.0 or higher handles wireless programming. Expansion happens through the standardized Technic pin and axle system. Kits integrate across product lines if you understand mechanical compatibility constraints. The curriculum framework component distinguishes this from consumer products. Lego Education provides 40-plus hours of scaffolded lessons per kit, aligned to next-generation science standards and Common Core math standards. This matters for homeschool documentation and credit validation. Now, let's talk about how Lego STEM education actually works. The learning architecture operates through three parallel development tracks: mechanical systems, programming logic, and sensor integration. Students don't build random structures, they solve constrained engineering problems with defined success criteria. The mechanical progression starts with initial builds focusing on gear ratios, lever mechanics, and structural stability. We Do 2.0 introduces simple machines like pulleys, gears, and cams.
Spike Prime advances to complex drivetrains, differential mechanisms, and load-bearing frame design. Technic kits push into pneumatics, linear actuators, and multi-degree of freedom joints. Each stage introduces one new constraint while reinforcing previous concepts. Programming integration starts with block-based coding focused on sequential command execution: move forward, turn, stop. Complexity layers through conditional logic with if-then statements, loops, variables, and eventually functions. Spike Prime's Python bridge exposes actual syntax. Students see their block code rendered as Python script, creating a visual Rosetta Stone for text-based languages. I ran my own children through this exact curriculum. The transition point where block coding becomes limiting happens around 80 to 100 hours of build time. Students start wanting nested functions and custom libraries, capabilities that require text-based environments. Spike Prime's dual interface handles this gracefully. Older EV3 required a hard jump to a new IDE. Sensor-driven decision-making is where actual systems integration begins. A light sensor triggers LED color changes, which is simple input-output. A distance sensor modulates motor speed based on proximity. That's proportional control. Multi-sensor arrays create autonomous navigation. Ultrasonic for obstacle detection, gyroscope for heading correction, color sensor for line following. By Spike Prime Level 3, students build state machines with 5 or more sensor inputs informing real-time motor adjustments. For lab implementation, each kit requires dedicated workspace. You need a minimum 24 by 36-inch building surface, nearby power access for charging, and a component organization system. Those small Technic pins disappear instantly. Plan for 45 to 90-minute uninterrupted sessions. Context switching kills momentum. Projects don't pack down well mid-build, so permanent or semi-permanent space matters. The expandability architecture is important to understand. LEGO education kits ship with 280 to 560 pieces depending on platform. Expansion sets add specialized components like large motors, advanced sensors, and pneumatic systems. Cross-compatibility exists, but requires understanding Technic versus system brick integration. Spike Prime uses Technic frames with system brick compatibility. You can incorporate standard LEGO elements, but structural loads require Technic pin connections.
For consumables and ongoing costs, rechargeable batteries degrade after 300 to 500 charge cycles. That's 18 to 24 months of heavy use. Replacement hub batteries run $30 to $40. Technic pins and axles are technically consumable. They don't break, but they disappear. Budget $40 to $60 annually for component replacement in active learning environments. The curriculum delivery model offers flexibility but requires instructor investment. Lesson plans provide structure, but effective facilitation demands adult understanding of mechanical principles and programming logic. LEGO Education offers certification programs that are online, self-paced, and free. They're worth the 8 to 10 hours for anyone running home lab implementations. Moving on to why LEGO STEM education matters. The skills gap between secondary education outputs and entry-level engineering requirements widens significantly between 2020 and 2025. Employers consistently cite deficiencies in 3 areas: systems thinking, which is understanding how subsystems interact; debugging methodology, systematic troubleshooting and documentation practices, communicating technical decisions. LEGO STEM education specifically addresses these gaps through its constraint-based problem architecture. For career pathway alignment, the progression from block coding to Python directly mirrors professional embedded systems development workflows. Arduino programming, Raspberry Pi automation, and industrial PLC configuration all follow similar logic structures. Students who complete Spike Prime's advanced curriculum transition to Arduino robotics platforms with minimal friction. They already understand PWM motor control, sensor polling rates, and interrupt handling at a conceptual level. Here are the measurable competency milestones.
By 120 hours with Spike Prime, students should independently design gear trains achieving specific speed ratios. That's mechanical engineering. They should write 100-plus line Python programs with functions and error handling. That's software. They should calibrate multi-sensor arrays for autonomous navigation, systems integration, and they should document build instructions and code logic for team handoffs, technical communication. These aren't abstract benefits. When my daughter applied to a competitive STEM high school program, her portfolio included a Spike Prime autonomous warehouse robot project. The admissions interview focused on her debugging process when the gyroscope drift caused navigation errors. That was exactly the systems thinking they wanted to see.
For industry tool exposure, Spike Prime's Python environment isn't educational Python. It's actual Python 3.x with standard library access. Students learn authentic syntax, not a simplified dialect requiring relearning later. The CAD-style building approach, planning assemblies before construction, parallels Fusion 360 and SolidWorks workflows. Understanding mechanical constraints in physical builds translates directly to 3D design environments. Let's talk cost per skill hour analysis. A Spike Prime kit, which runs $330 to $380, delivers 150 to 200 hours of structured learning before students exhaust the curriculum. That's $1.80 to $2.50 per learning hour. That's competitive with consumable-dependent platforms and superior to subscription coding platforms at 100-plus hour timeframes. The durability factor matters for ROI calculations. We're 400-plus hours into our Spike Prime kit with one motor replacement at $25 and one hub battery replacement at $35. ABS plastic components survive repeated assembly and disassembly. Compare this to electronics breadboard kits, where components fail after 20 to 30 insertion cycles, or 3D printer filament costs, accumulating at $15 to $25 per significant project. Now let's cover the types and variations in LEGO STEM platforms. Understanding platform differentiation prevents expensive mismatches between student capability and system requirements. Each LEGO STEM line targets specific age ranges and skill development focuses. LEGO Education We Do 2.0 is for ages 7 to 9, with a base kit running $160 to $180. It's the entry point for motor control and basic sensors. You get a single motor, motion sensor, and tilt sensor. It runs proprietary block-based software, a Scratch derivative. Builds focus on simple machines, lever systems, pulley mechanisms, gear demonstrations. The limitations are significant. It can't transition to text-based coding, and students outgrow it quickly, typically in 60 to 80 hours. Best use is introducing cause-effect programming logic before reading fluency develops. LEGO Spike Essential for ages 6 to 8 and $230 to $260 is the We Do replacement released in 2021. You get 2 motors, a color sensor, and a light matrix display. Same software limitation, block coding only, no Python bridge. The curriculum emphasizes storytelling integration with engineering, like building characters that solve problems. It's useful for schools prioritizing literacy STEM integration, less valuable for pure technical skill development.
LEGO Spike Prime, ages 10 to 14 and $330 to $380, is the core platform for progressive LEGO STEM education. You get 3 motors, 2 medium and 1 large, plus distance sensor, color sensor, force sensor, and a 6-axis gyroscope. The critical differentiator is the dual coding environment, block-based or Python. The hub runs a dedicated processor, an STM32F413 with 320 kilobytes RAM and 1 megabyte flash storage. Expansion sets are available for $80 to $120. This is the sweet spot for home lab implementations. It has sufficient complexity for 200-plus learning hours, an authentic programming environment, and it's ready for competitive robotics. First LEGO League uses Spike Prime. LEGO Mindstorm's Robot Inventor for ages 10 and up was discontinued in 2024 but is widely available.
It's the EV3 successor targeting the consumer market. You get 4 motors, a color and distance sensor, and a hub with speaker. It uses the same programming app as Spike Prime but lacks education's curriculum framework. The expansion path is unclear. LEGO shifted focus to Spike Prime for the education market. Only consider this if you find it significantly below Spike Prime pricing. Otherwise, Spike offers a better support ecosystem. LEGO Technic sets, ages 9 and up and ranging from $30 to $500, focus on mechanical engineering, typically with no electronics. You get advanced gear systems, pneumatics, and complex linkages. Use these for understanding mechanical advantage, structural engineering, and load transfer before adding programming complexity. High-end Technic sets like the Liebherr Crane or Bugatti Chiron demonstrate professional CAD to physical product workflows through their assembly instructions. For platform migration strategy, start with Spike Prime unless your student is under age 8, in which case start with WeDo or Spike Essential. Skip intermediate steps. The capability ceiling matters more than perfect age alignment. Supplement with Technic sets for mechanical concept reinforcement. After 150 to 200 hours with Spike Prime, transition to Arduino platforms or Vex robotics for industry-standard electronics and metal construction. Let me walk you through building a progressive LEGO STEM learning path. Effective LEGO STEM education requires structured progression through defined capability milestones, not random project selection. The framework below represents 18 to 24 months of development for a motivated 10 to 12-year-old investing 3 to 4 hours weekly.
Phase 1 is Mechanical Fundamentals, weeks 1 to 8, 25 to 30 hours. Complete Spike Prime Unit 1 curriculum focusing on structural integrity and basic mechanisms. Key builds include a driving base for gear ratio understanding, a grabber mechanism for linkage design, and a crane system for pulley mechanics. Success criteria: the student independently calculates gear ratios for specific speed and torque requirements and troubleshoots structural failure points without prompting. Phase 2 is sensor integration, weeks 9 to 16, 30 to 35 hours. Progress through units 2 and 3, adding sensors to mechanical builds. The critical milestone is an autonomous line-following robot using color sensor feedback and proportional steering control. This reveals whether the student understands closed-loop systems versus sequential programming. Many students plateau here. They can follow instructions but struggle with independent sensor calibration. Push through with systematic debugging practice. Document sensor readings, test hypotheses about threshold values, iterate calibration parameters. Phase 3 is the Python transition, weeks 17 to 24, 35 to 40 hours. Switch from block coding to the Python environment. Initial projects replicate previous block-based builds in text syntax. Spike Prime's side-by-side comparison view is essential. Students see their blocks convert to Python, building translation skills. Focus on functions, variables, and basic libraries before attempting new projects. Students ready for this phase can explain what a variable stores and why functions reduce code duplication. Phase 4 is Complex Autonomous Systems, weeks 25 to 40, 50 to 60 hours. This covers multi-sensor state machines, competition-style challenges, and custom project development. An example is a warehouse automation robot that navigates a maze, identifies colored objects, and sorts them to designated zones. This requires sensor fusion, distance plus color plus gyroscope, state management with searching, approaching, grabbing, and delivering states, and error recovery. What happens when an object isn't where expected? Phase 5 is competition preparation or custom engineering, week 41 and beyond, 60+ hours. There are 2 paths here. First, LEGO League competition participation teaches teamwork, documentation, and presentation skills alongside technical capability. Or independent project development. Create something novel, document the engineering process, present findings. Both require competencies beyond programming, project management, technical documentation, and iterative design methodology. For integration with a broader STEM path, LEGO platforms sit between screen-free coding fundamentals and text-based robotics programming. They offer physical feedback that pure software environments lack while maintaining expandability that fixed-function robots don't support. After exhausting Spike Prime's capability ceiling, students possess prerequisite skills for Arduino C++, Raspberry Pi Python automation, and entry-level CAD software. I've observed some common failure modes. Skipping mechanical fundamentals to jump directly into programming results in unstable robots and debugging confusion. Abandoning projects when initial code doesn't work instead of systematic troubleshooting is another big one. Parent over-involvement in problem-solving prevents student development of debugging methodology, and inadequate documentation of successful solutions requires re-solving identical problems weeks later. The solution is to enforce documentation requirements from day one. Before moving to the next project, the student must create build instructions and code comments explaining their solution. This mirrors professional engineering practice and dramatically reduces learning friction. Now let's cover lab specs for LEGO STEM implementation. Effective learning requires appropriate infrastructure. These specifications come from running intensive home lab sessions with multiple students over 400+ hours. For physical workspace requirements, you need a minimum surface of 24 by 36 inches of stable table space, ideally 36 by 48 inches for complex builds. For storage, you need an organized component system, minimum 6-compartment container for Technic pins, axles, and connectors. Tackle boxes work well in the $15 to $25 range with adjustable dividers. Power access should be within 6 feet for hub charging, with a USB power adapter at 5 volts and 2 amps minimum. For lighting, you need overhead plus task lighting, minimum 500 lumens at the work surface. Color sensors need consistent lighting for reliable readings. And a flooring consideration, carpet loses small components permanently. Hard flooring is recommended, or use a large work mat over carpet. Computing requirements include hardware that meets minimum OS requirements, Windows 10 and higher, Mac OS 10.14 and higher, or Chromebook running Chrome OS 90 and higher. The tablet option is an iPad with iOS 10 and higher or Android tablet with 5.0 and higher. Minimum 9.7-inch screen for a usable interface. Bluetooth version 4.0 or higher is required for hub connectivity. Most devices from 2018 and later are compliant. For storage, you need 500 megabytes for the application plus 100 to 200 megabytes per student project documentation. And for network, initial software download requires internet, but all subsequent operation is fully offline.
Spike Prime's specific specs include a hub with 6 ports, 4 for medium motors or sensor ports, 2 for large motor ports. It has a programmable light matrix at 5 by 5, a 6-axis gyroscope, and a speaker. The battery is rechargeable lithium-ion 2100 mAh with 8 to 10 hours runtime and 3 to 4 hour charge time via USB-C. The motors include a large motor at 850 degrees per second and running torque of 25 Newton-centimeters, and a medium motor at 1400 degrees per second and running torque of 8 Newton-centimeters. The speed versus torque trade-off teaches mechanical engineering principles. Sensors include ultrasonic distance with 4 to 250 centimeter range and plus or minus 1 centimeter accuracy, a color sensor with 8 color detection and reflectivity mode from 0 to 100%, and a force sensor with 0 to 10 Newton range. Connectivity is Bluetooth only, with 10-meter range typical. A USB-C cable is included for wired programming during initial setup or Bluetooth troubleshooting. For expansion pack considerations, the Spike Prime expansion set runs $100 to $120 and adds 603 additional pieces, including specialized elements like large wheels, complex gears, and structural frames. It's necessary for advanced projects, but not required for the first 80 to 100 hours of curriculum.
Prioritize it if pursuing competition robotics, otherwise delay until the student completes base kit projects. Durability and maintenance expectations include an expected lifespan of 400 to 600 hours before component replacement is needed, assuming proper storage. Wear items are motor gears, with replacement running $20 to $28 per motor after 300+ hours of heavy use, and the hub battery at $30 to $40 at 18 to 24 months. Common failures include Technic pin loosening in frequently assembled joints and axle stress cracking at high load connection points. For prevention, rotate which pins and axles get used in high-stress applications, avoid over-tightening connections, and store in a consistent temperature environment, not a garage in temperature-extreme climates. Software version considerations: LEGO Education maintains the Spike Prime app with backward compatibility to original 2019 hardware. Updates add features like improved Python libraries and expanded block coding options without breaking existing projects. Unlike consumer robotics platforms with frequent software overhauls requiring project migration, Spike maintains 4+ year stability. Updates are optional but recommended. Bug fixes and improved sensor calibration routines matter.
For multi-student implementations, one SPI Prime kit supports 2 to 3 students collaboratively. Beyond that, motor and sensor sharing creates bottlenecks. 4 to 6 student groups need 2 kits. Component mixing is allowed. Students can combine elements across kits for larger projects, though this requires coordination and advanced organizational systems. For integration with other platforms, SPI Prime components are physically compatible with all LEGO Technic elements and standard LEGO system bricks via Technic-to-System adapter pieces. Electronic compatibility is limited to the Spike ecosystem. You can't use Arduino sensors with the Spike Hub. This is intentional design isolation maintaining age-appropriate complexity. After outgrowing Spike, transition to Arduino environments for open architecture sensor integration. Let's talk about skills progression and capability milestones in LEGO STEM education. Vague age ranges provide minimal guidance. These concrete milestones define what proficiency looks like at each stage, enabling objective assessment of student progress. Milestone 1 is mechanical assembly competency at 20 to 25 hours. The student independently follows digital build instructions, identifies correct pieces from visual reference, and executes 40+ step assemblies without adult intervention. They demonstrate understanding that structural integrity requires proper connection sequences. They don't force pieces and recognize when a frame isn't square. Tests: can the student troubleshoot why a gear train binds? Do they check for correct pin insertion depth before declaring a build broken? Milestone 2 is basic programming logic at 35 to 40 hours. They write block-based programs with 15+ commands, including loops and basic conditionals. They understand that computers execute instructions sequentially, that loops repeat code blocks, and that conditional statements create decision points. They create simple sensor-responsive behaviors. Robot stops when detecting an obstacle, changes direction when seeing a specific color. Tests: can the student explain why their program didn't work and propose a specific fix? Do they grasp cause-effect relationships between sensor readings and motor commands? Milestone 3 is systematic debugging methodology at 55 to 65 hours. When a program doesn't work as expected, the student follows a diagnostic process. Isolate which component isn't behaving correctly, test that component independently, form a hypothesis about the cause, test the hypothesis through targeted code changes. They maintain a change log documenting what modifications were attempted. They use print statements or LED indicators to verify variable values during execution. Test: present a partially working robot with a subtle error, like a sensor threshold set incorrectly.
Does the student methodically test components or randomly change values, hoping for improvement?
Milestone 4 is Python syntax proficiency at 80 to 100 hours. They write Python programs of 50-plus lines with functions, variables, and imported libraries. They understand indentation requirements, basic data types like integers, strings, and lists, and function parameters and return values. They translate block-based programs to text syntax without side-by-side reference. Tests. Can the student write a function that accepts motor speed as a parameter and returns calculated distance traveled? Do they understand scope, why variables defined inside functions aren't accessible outside? Milestone 5 is multi-sensor system integration at 120 to 150 hours. They design autonomous robots using 3 or more sensors simultaneously and implement state machines managing robot behavior based on sensor combinations. They calibrate sensors for environmental conditions. Light sensors behave differently under fluorescent versus LED lighting. They create robust behaviors handling edge cases. What should the robot do if a sensor reads an unexpected value? Test. Student builds a competition-style challenge robot that navigates an unknown course, adapts strategy based on discovered obstacles, and completes the task without human intervention. Career-relevant capabilities at completion. Students finishing this progression possess foundational skills for robotics engineering, mechanical design, sensor integration, and autonomous behavior programming. They're ready for embedded systems development, microcontroller programming, hardware-software integration, real-time control systems. They understand manufacturing automation, robotic material handling, quality sensing, process sequencing. And they have product design skills, CAD-style assembly planning, constraint-based engineering, and iterative prototyping.
The gap between Spike Prime mastery and entry-level engineering internship eligibility narrows considerably. Students still need calculus, physics, and advanced programming, but they possess practical systems integration experience most university freshmen lack. 3 of my daughter's high school classmates who followed similar paths secured summer positions at automation companies specifically because they could demonstrate hands-on robotics experience during interviews, not just theoretical knowledge from classroom STEM courses. Let me wrap up with some frequently asked questions. First, what age should students start LEGO STEM education programs? Students should begin structured LEGO STEM education at age 7 to 8 with platforms like WeDo 2.0 or Spike Essential if they possess basic reading comprehension and can follow multi-step instructions independently. Though most students achieve better long-term outcomes starting directly with Spike Prime at ages 10 to 11, when abstract thinking capabilities support understanding variables, conditional logic, and systematic debugging methodologies that define actual programming competency, rather than simple command sequencing. Does LEGO STEM education require ongoing subscription costs? LEGO STEM education platforms require no mandatory subscriptions for core functionality. All software downloads free from LEGO Education, operates entirely offline after initial installation, and includes full curriculum access with kit purchase, though optional expansion packs run $80 to $120. Replacement consumables like hub batteries every 18 to 24 months cost $30 to $40, and motor replacements after 300-plus hours intensive use cost $20 to $28 each. Families should budget approximately $60 to $100 annually for active learning implementations. Can LEGO robotics platforms teach real Python programming? Spike Prime and Robot Inventor platforms teach authentic Python 3.x syntax with standard library access, including math, random,
time and U-time modules. This enables students to write actual Python code executing on the hub's embedded processor, rather than simplified educational dialects, though the development environment provides scaffolding through autocomplete and error highlighting that production Python IDEs may not offer, creating minor transition friction when students advance to professional development tools like VS Code or PyCharm.
How does LEGO STEM education compare to VEX robotics for skill development? LEGO STEM platforms prioritize rapid prototyping, mechanical iteration, and accessible entry points for ages 10 to 14 through tool-free assembly and block-to-Python coding progression. VEX robotics systems target ages 13 and up, with metal construction requiring actual tools, C++ text-based programming from the start, and competition-focused curriculum that builds toward industry-standard robotics engineering. But VEX demands significantly higher initial adult facilitation and troubleshooting support. What's the expected lifespan of a LEGO Spike Prime kit with regular use? A Spike Prime kit supports 400 to 600 hours of active building and programming before requiring significant component replacement, assuming proper storage and handling. Rechargeable ALB batteries degrade after 300 to 500 charge cycles, typically 18 to 24 months of intensive use. Motors occasionally require replacement after 300+ hours at high loads, and structural pieces like Technic pins and axles remain functional indefinitely, unless lost. This makes the per-hour learning cost approximately 60 cents to 95 cents when including reasonable expansion and maintenance expenses over a 3 to 4 year active learning period. So here's the summary. LEGO STEM education delivers measurable technical competencies through structured progression from mechanical assembly through Python programming and autonomous systems integration. The platform differentiation matters. Spike Prime represents the optimal entry point for ages 10 to 14, providing 200+ hours of curriculum before hitting the capability ceiling, authentic Python syntax enabling direct transition to industry-standard tools, and expansion architecture supporting competitive robotics or custom engineering projects. The investment framework is clear: $330 to $380 for the base kit, $60 to $100 annual maintenance, and dedicated workspace with a computing device and organized storage. The return is systematic debugging methodology, hardware-software integration fundamentals, and a demonstrable project portfolio distinguishing students in competitive STEM program applications. Implementation requires adult understanding of mechanical principles and programming basics, minimum 3 to 4 hour weekly dedicated sessions, and enforcement of documentation practices that mirror professional engineering workflows. Students completing this progression possess prerequisite skills for Arduino development, CAD design systems, and entry-level automation engineering. These are capabilities directly aligned with current industry hiring requirements rather than abstract STEM exposure.
The platform works when matched to student readiness and supported with structured progression. It fails when used as entertainment, implemented without workspace infrastructure, or abandoned at the first debugging frustration. For families committed to developing actual technical capabilities rather than accumulating educational toys, LEGO STEM education represents one of the few systems delivering both measurable skill development and clear pathways to industry-standard tools. That wraps this episode of the STEM Lab podcast. Thanks for spending this time with us. New episodes drop every Monday, Wednesday, and Friday, so there's always something new coming your way. If this one helped you out, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It's not just vanity metrics, it actually helps other parents and educators find the show when they're searching for real guidance on STEM education. And definitely subscribe or follow if you haven't yet, so you get notified the second a new episode goes live. See you next time.